In the previous tutorial, we learned about trapezoidal method of integration. In this tutorial, we are going to look at another method called Simpson's rule of integration, which is slightly better than the trapezoidal method. So let's get started. So firstly, let's have a comparison between these two methods. In trapezoidal method, we were approximating the function using lines. So if you see the upper line of this triangle, it is a line, and this fails to capture the curvature of the function that we are trying to calculate area under. So can we do something better? Instead of having these straight lines, can we do something better? And that's where we replace these triangles with parabolas. And since parabolas are not straight lines, they are allowed to curve. They are in a better position to approximate curvatures rather than straight lines. So that's the essence of Simpson's rule. Instead of using trapezoids like this and straight lines like this, it uses parabola to hug the curve and try to calculate the area under the curve. That's the main difference. Otherwise, the rest of the approach remains the same. So let's have a visual feel of it. Assuming that we have a function called x3 minus 2x plus 1, which is depicted by this blue line, and we are required to calculate its area from -1 to 2. So the green shaded area, what you're seeing here, is the area under the curve, and this is what we are required to calculate using Simpson's method. So as I mentioned earlier, Simpson's method uses parabolas to approximate this area under the curve. So we start with very elementary method, in which we just take one parabola, which is depicted by this orange dashed line. This is just one parabola, which is trying to mimic the behavior of fx, the original function in blue. So obviously, this orange parabola dashed line, the area covered under it is shown here in red color. And clearly you see that there's a big difference between the green area and the red area. And that's because we are just using one single parabola, and also the interval is very large. So let's overlap both these figures together and see what is not being captured. So as you can clearly see that the parabola, this orange dash line, is unable to capture this green shaded area, which is part of the original function. So, also, this area here is also not captured by the parabola. Whatever that we are seeing in the dark brown color, that has been captured by the parabola. But in addition to capturing this, it has also added area of its own, which was not, which is shown here in red color, both these segments, which are not part of the original area under the curve, as given in this blue curve. So clearly, there are two things that we can learn from this. One is that one single parabola is not sufficient to approximate the whole curve, number one. And secondly, this interval plays a role. So let's try to reduce this interval. So let's see this interval from minus 0.5 to plus 0.5, and here we see that approximately this parabola is trying to remain under the main curve and is trying to approximate the area more or less correctly. So let's just focus on this region here. So now I have changed the axis. I've zoomed in. I'm zooming from minus 0.4 to plus 0.4. And what I've done here is I've taken the original function, which is this one, x cubed minus 2x plus 1, which we are trying to integrate. And the green shaded area is again the same thing. It's the area under the original curve. Let's see what's the area under the orange curve. So now you can see that there's this orange dash line, which is a portion of this parabola, not the complete parabola, but a portion of it. And the interval has been reduced from minus 0.4 to plus 4. And as you can see that both these lines are very closely overlapping with each other. And we can see it from this graph that if we just consider this section, that is from minus 0.4 to plus 0.4, a parabola appears to be a very good approximation of area under the curve of the original function fx. So as you can see that the interval plays a major role. What about the number of parabolas? So let's see it in the next slide. So this blue line is a x cube function, and we are trying to capture the area under this curve. So earlier I had approximated one single parabola. I've used one single parabola to approximate the function. Now in this slide I'm using 6 parabolas, and as you can see that on piecemeal basis these parabolas are trying to approximate this function. For example, this parabola number 1 is overlapping here, and then parabola number 2 is overlapping here, parabola number 3 is overlapping here, and so on and so forth. Though it's not an exact and accurate approximation, but with the 6 parabolas, this is the best that we can do. So let's increase the number of parabolas, and now we have 12, and this is a much better approximation of this function than the previous one. Let's see the next one. This is 24 parabolas, and as you can see that we are getting closer and closer, more accurate in our estimation of area under the curve. This is with 48 parabolas, 96 parabolas, and 192 parabolas. So you see that the more the number of parabolas that we use on a piecemeal basis, we are able to approximate this curve in a much better manner. So what we are trying to do is use a parabola which is a quadratic equation like ax square plus bx plus c, and at any given instant of time we are trying to integrate it under the limits minus h to plus h, which you can roughly equate it to 2 dx. This is dx and this is another dx of integration, and under these limits we are trying to calculate the area under the curve, and we are hoping like hell that this matches with the original function that whose area we are trying to capture by using this proxy parabola on top of it. So I hope you got the picture. So let's start with a function called fx. It is required to be integrated between a and b, not minus h and plus h, between a and b. So our Simpson's rule says that this whole process can be approximated by a parabolic function, and that parabolic function is required to be integrated in subintervals from minus h to 0 and 0 to plus h, and then we are going to use multiple such parabolas to approximate this area of original function under the curve. So this whole expression can then be broken down into 3 parts. So the first term can be taken out independently, the second term can also be taken out independently, and the third term is also taken out. And we are going to integrate each one of them from minus h to plus h. So let's start with the first term. It's a even function. So even functions are, because of the squaring action, there's going to be no negative component. So as we can see here, when x is positive, the area under the curve of x square is positive. And even when x is negative, it has a positive area. So all we are required to do is calculate area under the curve, not from minus h to plus h, but 0 to plus h, and then multiply it by 2, because both these areas are just the same. Now bx is an even function, is an odd function, and odd functions, when they are integrated from minus h to plus h, the areas cancels out. So here we can see that x is varying from 0 to plus 1, and we have got, because this is the equation of line, bx is just the equation of line, so area under it is positive. But when we go into the negative direction towards minus 1, the area under the curve is red. So when we add both of them together, both these areas they cancel out, and the net integral here becomes 0. So this component is not going to contribute anything in the calculation of the overall integral. And the last is a constant, c dx. So it remains constant throughout, and it's a even function. So in this case also, we have to just calculate the integral from 0 to the plus direction and multiply by 2 to capture this negative area, to capture the other side of the function. So this is the story. So instead of calculating minus h to plus h, we are just doing 0 to plus h and then multiplying it by 2. This whole function is not contributing anything, it turns out to be 0. And again, here we are calculating this integral from 0 to h and multiplying it by 2. So let's further simplify these two terms and see what happens. So let's start with this one. Ax square, integral of ax square is nothing but ax cube divided by 3. And then we are going to substitute h in it. So what we get is 2a h cube divided by 3. So, and 0 gives nothing here. And for the second term that we had in this equation, we integrated. So there was no component of x here. The integral of this whole thing becomes cx, and then x is replaced by h. So we are going to get 2ch. And then we are going to add these two terms together. When we add these two terms together and manipulate it a bit, what we get is the area under the parabola is h divided by 3 and multiplied by this expression. If you multiply h by this first expression, it will become 2ah cube, and this 3 comes under it. So it is this term that we are talking about. And then when this h goes here, it becomes ch, and 6 is divided by 3, it becomes 2, so which is 2ch, which is what this term is all about. So this is our equation number 1, and we'll revisit this equation very shortly. Coming back to the same picture again, we are trying to calculate the area under parabola within the limit minus h to plus h using the equation of parabola. So let's start plugging numbers. So in this equation, ax squared plus bx plus c, if I put the value of x as minus h, that means I'm trying to calculate y naught here, this point here. So I insert minus h in the equation, and what I get is a h square minus bh plus c, and what this is equivalent to is this point on the curve, which is y0. Then I make this x is equal to 0. So when I make x is equal to 0, both ax square and bx, these two terms are going to disappear, and what remains is c. And at this point, at this x, the y point is y1. So c is nothing, but it is equivalent to y1 point. And lastly, when I insert h in this equation, what I get is ah square plus bh plus c, and the point on function that we get is y2. So these are the three equations, and we can try to do some manipulations to these three equations. The first one is that I'm going to add equation 1 and 3 together, and the end result is that this bh is going to get cancelled out. This is what is depicted here. I have added these two equations, and what remains is 2ah square becomes twice, so multiplied by 2, and same is the case with 2c. C, it becomes twice, and this term cancels out, which is also equivalent to y0 plus y2. And then I further manipulate this equation. So this y0, y2 is, I add one more term in this, which is 4 times y1. This is the term that I add into it, which is nothing but 4c. So I take the same equation here, y0 plus y2, which is this equation. I just take this entire expression and insert it here, and I add 4c to it because I have added 4y1 here, and y1 is equivalent to c. And when I aggregate the factors, the net equation becomes 10ah square plus 6c. So just remember this, y0 plus 4y1 plus y2 is equivalent to this expression here. We have found this expression in the previous slide, if you remember. It was appearing here. So let's stitch these two results together. So this is what we had gotten after integrating the integral from minus h to plus h, integrating the parabola. And now after manipulation of equations, we get this. This part is same as the first equation, which means this expression here is equivalent to y0 plus 4y1 plus y2. And this is exactly what is the formula for Simpson's integration method. What it says is that you take point number 1, add it to point number 3, and give maximum weightage, that is weightage of 4, to point number, which is the middle one, y1. And then multiply the whole expression by h, which is the interval, divided by 3. So what it's saying is, take y0, add it with y2, and multiply 4 with y1, and add all of them together, multiply them by this h, whatever is the subinterval, divided by 3. So there are two subintervals here. You can see from minus h to 0 and 0 to h. Two subintervals put together make one complete interval. So we will now go and implement this in Python and see how this whole integration is working there.